Hello everyone, thanks for watching this video. I'm going to talk about our work, Contrastive Semi-supervised learning for underwater image restoration via reliable bank. Despite the remarkable achievement of recent underwater image restoration techniques, the lack of label data has become a major hurdle for further progress. In this work, we propose a mean-teacher-based semi-supervised underwater image restoration Semi-UIR framework to incorporate the unlabeled data into network training. We first introduce a reliable bank to store the best-ever outputs as pseudo-ground truth to guarantee the correctness of labels. In view of the confirmation bias problem, we incorporate contrastive regularization to prevent the overfitting on wrong labels. Underwater image restoration is an ill-posed problem. Many deep learning-based methods are designed to learn the restoration mapping on paired datasets in a supervised manner. However, existing underwater benchmarks have two non-negligible issues. First, lack of real data. There is a significant discrepancy between synthesized and real data as shown in Figure 1. Second, limited data size. Compared with ImageNet and COCO, underwater benchmarks only provide very limited amount of paired data. Meanwhile, unlabeled underwater images are easy to collect. Semi-supervised learning, which capitalizes on both labeled and unlabeled data for model training, is best suited in such scenarios. We are motivated to adopt the mean-teacher method as the basis. It consists of a teacher and a student model. The two differ mainly in how their weights are updated. The student is updated using gradient descent, and the teacher is updated by exponential moving average of the student. But the naive mean-teacher method suffers from two main problems. On the one hand, there is no guarantee that the teacher can consistently outperform the student. Wrong pseudo-labels may jeopardize the training of the student network. On the other hand, the commonly used consistency loss is based on L1 distance. The strict L1 loss can easily make the model overfit wrong predictions, resulting in confirmation bias. As a result, we specifically design a semi-supervised framework for underwater image restoration to improve the generalization of the trained model on real-world data. To solve the first problem, we build a reliable bank to store the best-ever teacher outputs so as to ensure the reliability of pseudo-ground truth. Meanwhile, we incorporate contrastive regularization to elevate confirmation bias. First of all, wrong pseudo-labels can potentially jeopardize the training of the student network. Figure 5 shows an example. Unreliable consistency can mislead the student's optimization direction. To address the issue, we propose a reliable bank to store the best-ever outputs of the teacher network during the training process. The details are listed in Algorithm 1. Then arises the obvious question: how to determine the quality of a prediction without the true label? We conduct an empirical analysis of several NR-IQA metrics to find the best possible one for underwater images. Given a degraded underwater image X and a paired clean image Y, we perform various linear combinations of them to get a set of images with different quality. Following the monotonicity law, we conduct experiments with 7 NR-IQA approaches on EUVP benchmark, as it covers a wide range of underwater scenes. As shown in Figure 8, music is the most in line with the monotonicity law. Therefore, it is selected to measure the reliability of the network's output. Next, the sample consistency loss can easily make the student model overfit on wrong predictions, resulting in confirmation bias. We thus introduce contrastive loss. Thanks to our proposed reliable bank, where the samples are potentially of higher quality than the student's outputs, we can take reliable label as our positive sample. Other settings follow the design of a dehazing method, AECRNet, in 2021. Last but not least, our student and teacher model are based on the same structure, AIMNet, to tackle the prominent issues with underwater images such as low contrast, color distortion, and blur. Illumination prior and gradient prior are effectively exploited. The restoration branch incorporates illumination prior to enhance the color and light source perception capabilities. The gradient branch is introduced to enhance the edge structure. Here is the quantitative results. Incorporating unlabeled real underwater images in training might emphasize the network to pay more attention to the real underwater scene. Figure 11 performs some qualitative results. We can observe that our approach can robustly restore various types of underwater images with natural color and rich details. Figure 12 shows examples of intermediate predictions of the teacher model and the student model. As the training processes, the student's outputs and teacher's outputs are improved simultaneously. Table 3 and Table 4 indicate the influence of using different data augmentation and different NR-IQA approaches, which is consistency with former details. This is the end of the presentation. Thank you.